Hello. What we're covering today is Newton's first law of motion. And we're also doing a little bit of history. So this first video is just going to be about Aristotle and Copernicus and Galileo, who set up the basis for Newton. Well, not so much Aristotle, because he was the guy who wasn't very good at physics. So we're going to talk about how Aristotle was wrong, because it shows how important experimentation is for science. So let's go look at this. And so let's look at Aristotle. So Aristotle lived 384 to 322 BC. He was a Greek philosopher, scientist, and educator, and he was a good observer of the natural world. Recently, there was a report about some observations he'd made about some shrimp or something, and people noticed that they were still accurate, that nobody else had noticed it, but Aristotle had noticed it, and that was more than 2,000 years ago. Anyway, he had the advantage of being Alexander the Great's tutor. So he received gifts from Alexander. As Alexander went around the world, he would send back samples of plants and things to Aristotle. Alexander didn't like him very much, though. But anyway, Aristotle's ideas, he felt that his big brain, he should be able to figure out everything just using his brain. And so he didn't do experiments. But he felt he should make up rules about things. So because he had a big brain. One of the things that he talked about that related to what we call physics nowadays was motion. And he felt that motion should be divided into two separate categories. What we call natural motion, or what he called natural motion, was the natural motion of objects towards their natural place. Now, he determined this by saying that he was one of the people who proposed the four elements: earth, water, fire, and air. And that is where we get the word element that we use for the periodic table, except the elements, of course, we have 180 now instead of 4. And so let's go look at this. And actually, there was a fifth element too. So if you've heard the movie Fifth Element. So what did he mean by natural motion? Okay, well, the idea was that earth, water, fire, air. Earth was the lowest of those levels. And then came water and fire and air. So objects had a natural place. And then up in space was the fifth element. Objects like the moon were made of what was called quintessence. Okay, the fifth element. Okay, so now he ranked these in levels. And so if you have a rock, for instance, that rock will fall down through the water, right? It'll fall down past the flowing water. So that made the rock, the earth element, lower than the water, right? And water falls from the sky, raindrops, okay? But fire, it goes upwards, right? Fire, the smoke goes upwards. But it doesn't go as high as the clouds. So air was higher. And then finally you would have something like the moon and space, and that would be the quintessence. So his idea was that natural motion was objects returning to their special level. So rocks fall downwards, smoke goes upwards, clouds hang out in the sky. And so the thing is that his students, of course, would question him. They would say, okay, a rock falls down very fast. But what about a feather? A feather drifts downward, right? Drifts downward like this. And they said, what is the difference? Well, he had an explanation of that because he had his big brain. So he said, well, that's because the feather is made up of a combination of earth element and air element. So it falls towards the earth, but it falls more slowly. So that was his explanation. Okay, and please remember he was wrong, all right? Um, so anyway, so anything going up and down, basically, that was natural motion. But Aristotle felt that sideways motion was what's called violent motion. It required a force. So violent motion requires a force. Not writing too well today. Okay. And the silent, that's the idea. He said things to the side require a force. And they require a sustained push or pull if they are moving sideways. Okay, well, think about rolling a ball. You start it rolling, and after a while, it comes to a stop usually. But you weren't pushing on it the whole time. So Aristotle's students noticed this also, and they were saying, like, Master, what is going on with something like an arrow? So the bowman shoots the arrow, and it goes through the air a long time before it hits the ground. So nothing is pushing and pulling on it after it has left the bow. So why does it keep going? So Aristotle thought about this and his big brain, and what he decided was, what's going on? He said, well, as the arrow moves through the air, it pushes air out of the front, and that goes around to the back and pushes on it. And so there is a force that keeps it moving. So that was his explanation for things that are moving and why they can keep moving for a while, even though there doesn't appear to be anything pushing on them. So anyway, and please remember that he is incorrect. There's not enough air being pushed out of the front. I mean, it would be at most equal to the amount in the back. So, and that doesn't happen. So that's not why things keep going. So to figure out why things were going, we have to go 2,000 years into the future, almost to Galileo. Okay, so what happened was that Aristotle's ideas, like a lot of ancient Greeks, were somewhat lost for a while, but his were recovered earlier, and people were astounded by his intelligence and his ideas. And what happened was that the Catholic Church decided to accept his ideas as the official religion science. And that became a big problem for our next scientists, because that meant that anybody who said Aristotle was wrong were saying the church was wrong. And in those days, that was a very serious offense to question the church, and you could be taken and tortured. So the Inquisition was not a joke. It was a terrible thing. And so there were people burned at the stake for basically saying, no, Aristotle's wrong. Okay, well, let's go on and look at some of our brave heroes of science here. And so one of these heroes is Copernicus. And Copernicus is the one who also went against Aristotle's teachings, because Aristotle said that there was a geocentric solar system. Geocentric means Earth at the center, geo for Earth. So the geocentric system places the Earth at the center, and then, of course, and the sun went around the Earth, and the moon, of course, and all the other planets went around the Earth. That's the geocentric system. Now, the thing is that what was difficult to explain at that time was something called retrograde motion. Anyway, Aristotle also said all celestial objects were perfect spheres. They were unchanging quintessence. Okay, so along came Copernicus, who, because of this thing called retrograde motion, which is the idea that because Earth is moving, then when we pass, so with the sun at the center, that's called a heliocentric. So this is geocentric. A heliocentric system, of course, has the Earth going around the sun. And it is true that the moon goes around the Earth. But the Earth goes around the sun, and also the other planets go around the sun, like Mars. And what happens, what's retrograde motion? As the Earth, which is going faster than Mars, moves past it, then what happens is that first you're seeing Mars ahead of the planet, then you're kind of seeing Mars equal, and then you're seeing Mars, and it looks like it's going backwards now. It's like a car passing on the freeway, right? If you're the car that's passing, from your point of view, the other car could almost look like it's going backwards, retrograde. So anyway, so people saw the planet Mars do this weird backwards motion for a while in the sky, and that's what they called retrograde motion. Now, for the heliocentric system, that's easy to explain because, just like I did, we're talking about the planet Earth moving faster than the planet Mars. But the geocentric people, what they decided was that Mars had a loop in it, an actual loop in its orbit. So they called that an epicycle. So the cycle was the main orbital path, and then there were epicycles. And then to get the numbers right, they had to add extra epicycles. Anyway, so it was a crazy system. And Copernicus said, hey, it's really much easier if we just say it's a heliocentric system. But he said it very quietly. He wrote to friends, and he talked to people, but he wouldn't publish because he was afraid of the church in many ways, even though he was a teacher in the church. He's a mathematician and astronomer, and he taught Sunday school, but he didn't want to publish. So finally his friends persuaded him to publish, and so he published his work in 1543 as he was dying. Okay, so let's go on to Galileo. So remember that date, 1543. Galileo was born in 1564. So the heliocentric system, that idea was out there. And so one of the things that Galileo did, Galileo, remember we talked about him as the first true scientist, the first one who did experiments, careful experiments, and published his work and encouraged other people to do the same experiments for themselves. Do it yourself, he would say. And so he did all sorts of experiments. He was Italian. He roamed all around Italy, teaching at various colleges, because they did have colleges in those days. And he studied inclined planes, which are ramps, so balls rolling on ramps. He studied falling objects. He studied pendulums. We're going to be talking about those as we go along. But also, he was the first person to build the best telescope. His telescope was 20 times better than anybody else's. He ground his lenses himself, of course, and he put it together very carefully. And he used it to look out into space, which most people were just looking around the world. He looked out into space. And what he saw there was amazing. He saw that the moon had spots on it, sunspots. The sun has spots on it. So there were sunspots. He saw that there were mountains on the moon. He also, and so one of the things is that this is saying that Aristotle was wrong. Objects in space aren't perfectly spherical and made of quintessence, right? That they shouldn't have spots and mountains. He looked at Jupiter and found moons, which was amazing. He could see with his telescope that there was Jupiter, and he saw little things that were in orbit around it. And every night he would go out and he would see these things change their position, and he eventually figured out there were 4 moons orbiting Jupiter, which also went against Aristotle, because Aristotle said everything should be orbiting the planet Earth. And then he saw the phases of Venus. And you might not think the phases of Venus would be that exciting, but what he saw was that not only did Venus have phases, which means that it has crescent phase and a full phase like the moon, but also that Venus, as it went around the sun, pretend this is the sun now, um, it got smaller, smaller and larger in his telescope. And that showed that it was circling the sun. And he was seeing it on the far side of the sun and on the close side, and he would see a crescent, Venus, and it was all very exciting stuff, but it did seem to show that Aristotle was wrong. And it supported Copernicus. So anyway, he got in trouble with the church. He was arrested, and he was found guilty after a trial that lasted several years. He was imprisoned for some of that, and then having been found guilty, they placed him under house arrest for the rest of his life. And they told him he couldn't teach and couldn't do research and couldn't publish. And brave Galileo continued to do some of that. Anyway, so he was an amazing guy, and he lived till 1642. So you might remember that number for later. Okay, so he set up the basis of physics, and so we'll keep talking about Galileo for quite a while because he did so much great work. Okay, now another thing that Galileo and Aristotle disagreed on was that objects fall with a speed proportional to their mass. So that means that something that is twice as heavy should fall twice as fast. So if I was dropping a ball that was twice as heavy, then it should fall twice as fast. That's what Aristotle said. Now, the thing is, this is really easy to disprove. But Aristotle didn't actually just go ahead and do the experiment by dropping a heavy thing and a light thing to see if they fell with different times. Now, so let's do the experiment. I'm going to grab a piece of paper. We don't need this calendar. Actually, we could. All right, and a book. Oh, sorry. Some of the equipment decided to rebel. Okay, all right, so let's see what we're seeing here. Let's pin this up. All right. Now, this piece of paper and this book, if I drop them, will they fall at the same time? Well, let's see. If I drop them, they didn't. The piece of paper hit the ground first. I'm sorry, other way around. The book hit the ground first, right? Okay, but let's crumple up this piece of paper and do it again. Okay, so dropping them. Okay, now you see that there was very little difference. The piece of paper crumpled up fell at the same rate as the book. And so if Galileo had Aristotle's experiments in hand, that would be one thing. But Aristotle didn't do the experiments. He just thought it was a good idea. He figured out in his big brain that, yep, that sounds good. Let's go with it. And so anyway, whoops. Camera tilt. There we go. All right. So let's go back to the unpin this. There we go. All right. So it's very simple to demonstrate that that's not true. That book was 800 pages, but it and the paper were falling at the same time. What Galileo figured out is that air resistance can make a difference because it's a force that is opposing the falling motion of an object. But if you don't have much difference in air resistance, then objects fall at the same time. So if air resistance is negligible, meaning that there's a small difference or there's no air resistance, like on the moon, then objects will fall at the same time. And so make sure you watch the video about objects falling on the moon. Anyway, so Galileo showed that these dropped objects fall at the same time, and you can show it too, right? Just try dropping 2 books and 1 book at the same time. Do they fall at the same rate? Well, yes, they do. And if only Aristotle had actually done that experiment, poor Galileo wouldn't have had to disprove him. Okay, but this is one of the things that Galileo was in such amazement of at his trial. He was like, look, it's really obvious, you can prove this yourself. And, he would do demonstrations for the court, and they were like, we don't care. Aristotle's still right. So anyway, very, very bad science. Okay, so Galileo also worked on what are called inclined planes or ramps. And he noticed that a ball that rolls down a ramp will go down, but then if you got another ramp where it goes up, it will try to return to its initial height. So its final position will be at the same height as its initial position. So then he thought, well, what happens if you had a ramp, even if you change the angle, right? Then it still tries to return. What happens if there's no up ramp? The ball would just keep rolling forever? And that was his idea, that since objects speed up when they go down a ramp and they slow down when they go up a ramp, then when the ground is flat, they should really not change their speed. So Galileo came up with this idea that in the absence of friction or other opposing forces, a horizontally moving object will just move forever. And the property of an object to resist changes in motion is called inertia. So an object keeps moving because it has inertia. It resists changing its motion. To make the motion change, you've got to have a force. So a ball will just keep moving forever till a force changes it. And so you roll a ball, and eventually it comes to a stop, but usually that's because it hits something. But there's also friction from the floor, and there's some air friction. So eventually it does come to a stop, but those are forces. And Galileo was the first person to really recognize that it was the forces that brought it to a stop, not that it was its natural place to come to a stop. The idea of things moving forever without a force, that's Galileo. Is it true? Oh, yeah. We have spacecraft that we have sent out into space that were sent out 50 years ago. They were sent out in the 70s, and they're still going. And their motor hasn't worked in 49 years. They just keep going through space, and the planet Earth just keeps going around and around the sun. Set in motion, it keeps going until a force stops it. So unless some giant asteroid comes along and crashes into the Earth, it will just continue pretty much at the same speed forever. Okay, although there are some things that there are other forces out there. Okay, so anyway, so Galileo figured out that objects will just continue to move. Now, inertia is this property of objects to resist changes in motion. So mass, so this 1 kilogram mass, when I'm shaking it, I have to apply a force to make it change its motion. If I just threw it, normally I would throw a lot of balls in class, then it would keep going, right? So this ball I can throw, and so it will try to keep going. But gravity's going to pull it down, right? So it's got to have a force to change its motion. Now, this is how you can shake your hands and get water off them, because what happens is that water droplets will try to move in a straight line once they leave the hairs. And so you shake your hands to make them move fast enough that they can't cling to your hands because of friction. And in water case, it has an adhesion also. So anyway, so we shake it, and you can see these water droplets leaving the dog and coming off. Now, this is why you can play some tricks sometimes. You know, you can put a stack of coins and pull a piece of paper out from under them, and the coins stay stacked. It's pretty amazing. And they also, it's why you can do the tablecloth trick. Now, I'm going to do this, but not at this moment because it takes some setup, so it'll be a separate video. And so anyway, the tablecloth trick is something that you can do at home. Maybe not with the best china to start with, but it does work. You've just got to find the right tablecloth and get it set up the right way. But the idea is that all of these objects have inertia. And so the heavier they are, the more inertia they have. And so they want to stay in place. And so they need forces to pull them out. And if you've got a smooth tablecloth, as you pull the tablecloth out, it doesn't apply a lot of force. So the objects stay in place. And this is why when you are driving a car and you have to come to a hard stop, you know, suddenly the dog runs out into the road. Well, what happens is that if you're not belted in by a seatbelt, your body will try to continue forward. You are already in motion. The car has brakes that you've pushed on to make it come to a stop. But if you're not belted to the car, then you're just going to keep going. And you'll try to continue at the velocity that you were already going at. So if your car was going at 30 miles per hour, so will be the velocity of your body will also be 30 miles per hour. Okay, so that's one reason to wear seatbelts, so that you're connected to the brakes, basically, and to the car. Okay, so that's the end of this section, and so we will continue with the rest of the chapter in a moment. Okay, so I'm going to stop this recording. Okay.